So because these electron homes are square, we've got a nice convenient way and a nice little illustration here to denote the total number of rooms. Well, you can just take n, all right, the number of stories here, and take that value of n and square it. So if you have a one-story house, it's just a single room, you have 1 squared, or one possible electron room, or one possible orbital, right? If you have a 2-story home, then you have this 2 by 2 square, and that 2 times 2, or 2 squared, gives you the total number of possible orbitals, which is 4. And we keep doing this as we go on to these larger orbitals. We see that this n squared rule holds, and with the housing, quantum housing analogy and this little square model, it hopefully becomes a little bit more intuitive and easier to keep these numbers in your head. Okay, so this is great. We've got each one of these labels, S, P, D, and F, corresponding to the different sublevels, corresponding to different stories in our electron home, and we've got a nice quick way, n squared, that gives us the number of orbitals in a given shell, right? And recall, the shell is determined by that value of n. Okay, so the last thing to do now is introduce our third quantum number, m sub l. Okay, so the values that m sub l take can once again be mapped back onto this housing analogy by putting zeros across the diagonal and then counting off both in the negative and positive direction from that 0 point, and just including all the integers until you get to the end of the house. And so now you can see that any given value of n sub l, m sub l, and n and l will give you a specific, unique label or address for an individual electron room. So for example, if I gave you an n, l, m sub l combination that corresponded to 3, 2, 1, you could come over here and say, okay, well, I know that I'm going to be in a 3-story house, okay? So I'm going to be looking at this portion, and it would basically have something that looks like this, okay? A 3-story house, and I know that I'm dealing with an L equals 2. So the L equals 2 level is going to be our outermost story of the house, denoted here in green. Okay, so now we're going to focus it in even further and look at just that L equals 2 level, and then come in finally and nail down a specific room by looking at the possible value of m sub l. Okay, so I'll put that in red here to highlight it. Okay, that final unique room highlighted in red is the room that corresponds to the 321 orbital address. So we have a nice pretty picture here. It's nice and symmetric. And once again, hopefully makes things a little bit easier to identify and appreciate the relationships between these different quantum numbers. Okay, now it turns out that we can actually take this quantum housing analogy a little bit further to explain another important part of these orbital solutions to the Schrodinger equation. So recall, when we have the Schrodinger equation here, h psi equals e psi, okay, I mentioned psi as being this orbital or electron room, and I didn't say much about these other terms that are showing up in this mathematical expression. Well, it turns out that this second term, E, denotes the energy. Okay? So with each one of these orbital solutions, there corresponds a specific energy that the Schrodinger's equation tells us, right? And so to appreciate the relative energies of these different orbitals, it turns out that we can, like I said, draw on this housing analogy. And so the principle is pretty simple. The more electron rooms you have, the larger house you're building, the higher the energy. So if we start off here at the bottom with a smallest possible house that we can make, a single-story house, we have only one room, right? One single s orbital, and that's going to be our lowest possible energy. Then, if we make a two-story house, right, our 2x2 setup, then we're going to, the result will be a home with higher energy, and so on and so forth as you add additional stories to the home. Okay, so to help you remember this, you can think about this. Like suppose you're living in a house with a bunch of roommates, okay? And I want you to think about what would be the higher energy, higher stress level environment. Would it be a house where you have only a single roommate? Or would it be a house where you have 4 rooms, each one of them can accommodate two roommates, so you'd have a total of 8 possible roommates. So 2 or 8 possible roommates. Well, if hopefully now you've been living with a house with 8 roommates, that sounds like quite a nightmare. But as you can imagine, that would be a much higher energy, higher stress environment, having 8 folks living in the house, 7 other roommates. Okay, and of course that will just continue as you go to these larger and larger houses. And for example, the next one is a 3x3, so you'd have a total of 9 different rooms. Each one can accommodate 2 electrons, so you'd go up to 18 total electrons living in the house. Even higher energy setup. Okay, so larger homes, higher energy. So we're showing energy increasing here on that y-axis. Now, of course, it gets a little bit challenging to draw out all those little boxes, so we're going to have to scale back from our housing analogy, and we're going to introduce a more canonical notation, a more standard notation for representing this sort of thing. And we do that by replacing the box with a single line. So if I wanted to represent, that previous diagram nice and succinctly by the different lines, I will just draw out a small, lowest energy electron home comprised of just a single n equals 1 electron home. If we want to go to a 2-story home, then we go to the n equals 2, and we have the s and possible p orbitals there, and so on and so forth. So the thing I want to draw out from this image is that every single room in that given house, whether it's a 3-story house, a 2-story house, or a 1-story house, all of those rooms are equivalent in terms of energy. In other words, one of the rooms isn't less stressful to live in than any of the others, if you're dealing with a hydrogen atom. So, of course, the hallmark of that hydrogen atom is, if you're neutral, a neutral hydrogen atom has only a single electron. So if we go back and follow our notation of designating electrons by a little arrow, then we can put that single electron in that hydrogen atom, for example, right down here in that smallest possible room, the least stressful environment, which is the 1s orbital. Okay, so here's our next housing rule. It turns out that you can never have an electron between 2 different rooms or between 2 different homes. They are always in a specific home, in a specific room of that home. So it's okay to put an electron here, or we could put an electron here, but you could even put it at a higher level, way up here at the 3D orbital, but you're never going to find it just floating around in some intermediate energy space in between. It simply doesn't happen. Okay? And again, I'm asking you to just sort of trust quantum theory here and accept that fact that according to quantum theory and these mathematical solutions, the only states in which these electrons can be found are states where those electrons are residing on one of in one of these rooms and one of these homes. Okay? Furthermore, if that electron wants to move between different homes, then that electron must either absorb or release energy. So if you want to move to a home with an increased number of stories, for example, if you're an electron sitting down here in a 1-story home and you want to end up here in a 3-story home, well, you're going to need energy in order to make that happen. oftentimes the energy will come in as electromagnetic radiation, something that we talked about again in a great deal in previous lectures. Of course, that energy could come from other spaces. So I know the Bohr model, I mentioned that the Bohr postulated that this energy is only coming from photons. There are other ways to excite these electrons, and get them to move upstairs to larger homes. But suffice it to say, whatever you're doing, you're going to have to put energy into that atom or molecule. Okay. And if you're up here in a multi-story home and you want to go down to a smaller home, say in this example from a 3-story to a 2-story, then you're going to be losing that electron, and that molecule will be losing energy, and that will result then in the emission of a photon oftentimes. Okay? And so in this way, these quantum mechanical principles, all boiling down to solutions to this mathematical equation, are allowing us to predict something that Bohr and many other scientists had a very hard time understanding. Specifically, why is it that we only see certain lines on these emission or absorption spectra? Okay. Well, once again, it comes down to this quantum housing rule. You can only see electrons in certain shells, and transitions between those shells are the only, they correspond to only distinct bands in that electromagnetic spectrum. Okay, so the Rydberg equation up here and the Bohr model down here allowed us to provide some quantitative predictions for some very specific and very simple atoms. And what we're doing here with quantum theory is basically providing a more robust and a very general description of why this is happening. In other words, our H psi equals E psi is answering the why. Now granted, this why is a bit abstract. And in some level, I just pushed off the answer to, well, we've got a mathematical solution, and this happens, this sort of quantization of the different possible states that electrons can reside in, the different possible orbitals, they are solutions to the Schrodinger equation. That is the why. And so once again, I'm going to ask you to just sort of accept things, just as they are for the time being, and rather than going into more details of what that actually means, just accept that fact that we have these discrete orbitals. They have these labels that allow us to talk about them, the quantum numbers, and each one of those orbitals has a corresponding energy. And we'll leave it at that for now. And now I want to shift our focus to what these orbitals actually look like.